Again, good afternoon, everyone. What's projectile motion? Projectile motion is a two-dimensional motion. Two-dimension means it will happen in the X and Y axis, okay? So what are we going to do today? We will study a projectile motion. That means having an example. Because this is online, we are going to use simulation to do the experiment. But I'm going to show you the real one, which we do in GIC lab in situation where we don't have the virus and we don't have online sessions, okay? But the data that we will be recording will come from the simulation, which you will do yourself. So what are the other objectives aside from studying projectile motion? We will calculate the initial velocity of the ball, okay? That would be in table 1. What else? We will determine, which is the same as calculate, what we call the horizontal range when we launch our projectile at different angles. And finally, we will calculate or find the maximum vertical height of a ball or a projectile also when we launch at different launching angles. So we're actually going to do all 4 of these objectives, okay? The apparatus, of course, this is the actual one in the lab, but the one we will do is simulation. So in your report, just copy this one and all of this, kullu, all of this, and you can have your report, okay? Let's go to the theory. So projectile motion, as I said, is a two-dimensional motion, which happens when an object is thrown or projected into the air near the Earth's surface. That's because projectile motion happens with the effect of gravity on the object, okay? Assuming that you throw an object at an angle and say that angle is theta, the object that you throw, the force that you applied, which causes the initial velocity, is actually straight. But the object will travel in a curve, okay? That curve is called the trajectory. That's the path of the projectile, okay? It's called trajectory. And the object that you throw is, of course, the projectile. Now, when the projectile moves, it will be pulled down by the gravity of the Earth. Therefore, the trajectory, the curve, is actually caused by the gravity of the Earth, okay? Now, let's differentiate the parts of the trajectory of a projectile. The highest point here from the ground is the maximum height. Now, if you throw the projectile from the level, that means without the original height here, the maximum height will be from here. Okay, the maximum height will be from here to there, like this. But if there is initial height, let's say you go from Jebel, and from Jebel you throw a stone, or from the top of your building you throw a stone, okay? You have to add y initial, that means the original height from where you are throwing, to get the total maximum height. X, on the other hand, here, that's what we call the maximum range, or the horizontal distance where the projectile will travel, okay? If you are throwing from the ground level, so let's say you are here from the ground level, your maximum range will simply be from the source, okay, up to where the object will touch the ground. But because in this illustration you are throwing from a specific height y initial, okay, because you are throwing from a specific height y initial, you will see that the object will continue to travel, and x is actually longer because you are throwing from a higher position, okay? So basically that's projectile motion. Now, there is one thing which you need to understand from projectile motion. And why is that? Again, we said that projectile motion is motion in 2 dimensions. Those 2 dimensions are, of course, the x and the y dimensions. The x dimension, if you remember our objects in equilibrium, is this one. When you throw the object at an angle theta, the initial speed or velocity is, of course, v naught, but the x component of the motion is actually V original cosine theta, this angle here, okay? And the Y component is, of course, the force, the effect of the gravity pulling down on the object. And you will see this clearly when we start the simulation, okay? What's the important part is that the horizontal and the vertical component of the projectile is actually not going to affect each of them, okay? They are independent. When we say independent, this one will not affect VOY, and VOY will not affect VOX. The X component of the velocity will not affect the Y component. The Y component of the velocity will not affect the X component, okay? Now you will see that later. Whenever we make projectile motion experiment, we always neglect, okay? We always neglect air resistance when we make calculation. Why? Because air resistance affects the movement of the object, especially if the object is big, okay? And whenever we do, we calculate the horizontal range. The rule that we use is this one. That's the rule to find the maximum horizontal range of our projectile. To find the maximum height or the velocity at any point of your projectile, we use equation number 2. And these equations are simple, simply the equations for velocity equation, okay, or distance equation. It is the same equation as we get from velocity and acceleration equations, okay? So to get the maximum height of a projectile, we use this equation. Which equation you are going to write in your theory is this? Number 1, okay? You will write also this too, if you want. The definition is there. This is the definition. This one is no need because simply we use this to get this equation, okay? And this one. So you will write how many equations? This is together. 1, you will write this. 2, you will write this. These are the 3 main equations that we are going to use, okay? Now, how are we going to do the experiment? Let me start by showing to you the video demonstration of this experiment, and I want you to listen. Let's see, somebody arrived. It's the same. Today we are going to do an experiment. Can you hear the video, the sound?
On projectile motion, we are going to study vertical height.
Let me go forward,
here,
okay?
A projectile launcher where I can change the angle by loosening the screw at the back here and then rotating, thereby changing the launching angle. The angle is determined by this angle indicator, which is positioned at the back or at the end of the projectile launcher. In front of the projectile launcher, we have 2 photo gates. The first photo gate will detect the projectile as it passes through, and it's indicated by this light. And then as the projectile passes through the second photo gate, it will be detected as indicated by this light here. Now the projectile we are going to use is a steel ball, which I have in my hand, okay? And how we install it is actually by placing the ball inside the muzzle and then taking a plunger, which is this one here on my hand, and then pushing the ball in, thereby compressing a spring. Now, the strength by which we can launch the projectile has 3 levels, 1, 2, and 3. As a precautionary measure, we are only going to compress the spring with one click, or basically the lowest setting. Also, for safety, you must be wearing safety glasses, as I am doing now. To launch the projectile, we have a trigger, which is this, okay? Now, I'm going to launch the projectile, which I placed inside the launcher. I'm going to block it with my lab manual so that it will not fly off the table. Make sure that the ball is not going to fall off the table so that you will not lose it. We are also going to use what we call time of flight accessory. Basically, it is a sensor where our projectile is going to land or hit. That is going to allow us to measure the time it takes for the projectile to leave the launcher and reach the ground. In order to pinpoint or determine where a projectile will land, we are going to use a piece of paper, which we are going to tape over our time of flight accessory, and then we are going to place a carbon paper. The impact is going to leave a mark on the paper, and from there we can measure the distance horizontal that is traveled by the projectile. Now let us begin. We are going to use a software called Capstone, and you will have a file which is available for you on the desktop. Open the file that says initial velocity of projectile. Make sure that your interface is on and that it is connected to the computer. Next, you want to set your projectile launcher at a specific launching angle. In this case, we are going to do 15, 30, 45, 60, and 75 degrees. Set your launcher or launching angle at 15 degrees.
You see, that's how the angle is adjusted, okay?
Once it's set, place the projectile inside the launcher. You must make sure that the angle doesn't change. Take the plunger and push the projectile in until you hear one click. In the first table, we are not going to use the time of flight accessory. We are only interested in the muzzle velocity or the initial velocity of the projectile.
Okay, let me explain what's going to happen. The two photo gates here will detect the motion of the ball, okay? As shown in the beginning of the video, when the ball passes, there is a light that switches on from the front of the photo gate. Now, the ball will travel between the two photo gates from here to here. The distance is 10 centimeters, 10 centi, okay? You have to change that distance into into meter. Now, let me show you the table, okay? Distance between the photo gates, this is equal to 10 centimeter. You have to change it into meter. Is that clear? Shabab, is that clear? Hello? Okay, I have only one student. 2, 3, 4, 5. That's good. Because I don't want you, Allah, you will send me messages again at 2 in the morning asking what is this, okay? So again, please, if you don't respond next time, I will not record the session for you. Okay, there you go. So this is 10 centimeters. Okay, we change it to meter. Is that clear? Now it's clear. Let's continue. What are we going to do next? Next, when the ball travels, okay, the computer will measure the time it takes for the ball to cross or pass through first and second photo gate, and it will be recorded on the screen. If you remember, I showed you the screen there. That's the time it takes and then the computer will calculate the velocity of the ball. That's the velocity of the ball or the projectile as it goes out of the cannon or the launcher, okay? So the data will be given to us, and this data, you will record it in your lab manual. So the time between photo gate, this one here, okay? And let's go back to the data sheet. Muzzle velocity that's measured, that means measured by the software, this one here, okay? And then finally, let's go back to the data sheet. Muzzle velocity calculated, this is the rule. You get, how do you calculate the muzzle velocity? Distance over time. Distance over time. Is that clear? Okay, let's watch the video, and I want you to record in your lab manual this part of the data and place it here at 15 degrees, okay?
Initial velocity 15 is the projectile inside the launcher. You must make sure that the angle doesn't change. Take the plunger and push the projectile in until you hear one click. In the first table, we are not going to use the time of flight accessory. We are only interested in the muzzle velocity or the initial velocity of the projectile. You can take your lab manual and you can block the projectile from flying off the table. What we will do is click Start to record, launch the projectile by pulling the trigger and taking a reading from your computer. Make sure that you click the Stop button.
Let's go back just a little bit.
And taking a reading from your computer. Make sure.
Okay, you will record this in your lab manual. I'll give you 5 seconds to record it. 4, 3, 2, 1, and that's it, okay? Let's go back to the lab manual. There you go. You have now the distance I already gave you. You have time, measured velocity. You have to calculate this and the percentage error in velocity. Now, if you need guide on how to calculate, this one, the rule is given, okay? What about percentage error? There is no rule. If you check in the data sheet, let me go down, okay? You actually have a guidance for the percentage error. In table 1, just go to calculation, okay? This is not for you to answer. There's no need to answer this. This is just note, okay? This is just notes for you to guide. This is just the rules, okay? For table 1, you will use this. What about table 2? Later you will have table 2 for this, okay? Ahmed, you got what? What did you get? You got in. Finally, I got in. Okay, okay. I will check your attendance later. I'll give consideration to everyone. Anyhow, you missed a little bit in the beginning, but it's okay. Yalla, Shabab, I will tell you now, if you change the angle from 15 to 30 degrees, what's gonna happen? Nothing. The velocity will be same. It will be the same. I will talk about the attendance later at the end, okay? It will be the same. It will be the same. All the value for velocity approximately will be the same. The angles will not affect the initial velocity of any projectile. In fact, just imagine if you are hunting, for example, you use a rifle, okay? You shoot a lizard in the desert, horizontal, or you shoot a bird in the air with the angle. The gun will fire with the same initial velocity. So that's the idea. Therefore, in your lab report, do not focus on table 1. You can actually cancel all the other measurements. Just make the record in 15 degrees. Is that clear? Is it clear, Shabab? Hello? Okay, good. Good. let's go to table 2. This is where the fun is, okay? In table 2, we are going to measure the horizontal range and the maximum vertical height of a ball at different launching angles. This in the video is shown how to do
that
it.
you click
Okay,
the stop button.
let me go.
And the picture and height angle indicates the pro. Next, make sure that the software have your, do not use it in the projectile. Click record on the software. And finally, launch the projectile by pulling the trigger. I missed it. Press the record button and launch. Now, the first thing you must do is to get back or catch the ball, remove the carbon paper, and on the time of flight accessory, you will see that there is a dot that is created by the impact of the ball on the surface of the carbon paper.
Okay, so what we did here is a full projectile motion. The ball travel from the launcher, okay, and hits this surface, and this surface will actually take the time it takes for the ball to travel, okay, the T, the time of flight as we call it. What else? From here, we can measure the distance that the projectile has traveled from the front of the launcher, from here, up to the dot which is left on the paper, okay? And that is done by taking a tape. So we take a tape or a meter stick, and then we measure the distance. That's the horizontal range. There is no way right now to measure the height, so the height, the maximum height is just calculated. But again, like I said, we cannot do this experiment now because of all the setup that we have. Instead, we are going to do this experiment by simulation. So I'm going to close this video now, okay? And I'm going to show you the simulation that we are going to use. So this is the simulation that we are going to use, and I want each of you to go to this link, okay? I'm going to paste the link on the chat. There you go. Just click on this link. This is from Colorado University in the US. Go to this link and open it in your computer. And also, I'm going to send you an offline copy. If you don't have internet later, okay, you can do it even without internet. I will send you the offline copy in your group chat. So here, where you want to go is to click Lab here. Okay, so click Lab, double click, and it opens a setup for projectile. Okay, here we have a cannon. As you can see, you can change the angle of the cannon, but the minimum is only 25 degrees. You can set the initial speed or V initial, V naught. Okay, you can put air resistance, but we don't want air resistance, of course. You can have gravity adjustments for moon or different planets, but we use the gravity for the Earth, 9.8 meter per second squared. And you can also change the size of the projectile and the material of the projectile. Like if you want golf ball, baseball, football, whatever it is. Let's take football, for example. Okay? Now, let's try it. How does it work? Set the angle. Let's say 60 degrees. Okay? And then fire. And the projectile flies off. What happens if it's too much far from the screen? You can zoom out. There you go. And you can also zoom in. Okay? There you go. And you will see that there is actually a way to understand the vectors that affect the projectile. Remember, I told you the x and the y components of the initial velocity is independent of each other. If we go to vectors down here, okay, and then we click velocity vectors, and we fire our projectile any angle, you will see that it will show you the vectors, okay? Now, we want to see the components, x and y. There you go, okay? It shows us the components of the vectors, x and y. Let's change the angle, clear everything maybe from there, and then pause it. you can see that at any point, the x component of the velocity, which is VO cosine theta, is always forward. And look at the y component, okay? The y component of the velocity. The y component starts going up, and then upon reaching the highest point, the y component goes down. Why is that? Because the object in the y-axis, the projectile in the y-axis, is affected by gravity, okay? That's why the behavior or the motion is a curve. That's because of the gravity. What are the other things? Oh, I forgot to remove air resistance. There will be some difference with the air resistance, of course. Why is it that, what is it that we can do with our projectile? We can actually measure the range, x, as well as the height, as well as the time of travel by using this tool here, okay? This tool is just like the SMART tool. If you remember the SMART tool, okay, anywhere you place the SMART tool, it gives you the values that you need. In this case, if you place the tool here at this point, it gives you the time of travel and the range, okay? But the height, of course, is 0. If you place the tool here, the maximum height, you can see the dot is actually different color. It gives you the maximum height, okay? What else can we do with the simulator? You can change the height to give our cannon an initial velocity. An initial height, okay? So let's try it. If your cannon has an initial height, like I said, let's use the tape measure, okay? This is a tape measure. The maximum range will be more than when your cannon is from the ground. There, okay? You see how we can use the simulator, Shabab? Now, what are we going to use in our lab for this activity? We will use this one, lab, down here, okay? How are we gonna do it? First, let me split my screen. 1 second. One here. Come on. One here and one here, okay? You can still see the table, right? Let me zoom in a little bit more. Okay, here's what we are going to do. First, instead of 15 degrees, we are going to change this into 25 degrees. Clear? So instead of 15 degrees, we are going to change our angle into 25. Where's my typewriter? Class, I'll just write it. 25 degrees, okay? The others, you can keep the same number. It's fine. Then you will set your cannon at the given angle, okay, 25 degrees. But the initial speed that everybody is going to use, okay, the initial speed, that's the muzzle velocity, is always going to be 20 meters per second. Everybody will use 20 meters per second. The launching height, y initial, we will all launch from 0 so that we can cancel this in the equation, okay? So the launching height will always be 0. The initial velocity will always be 20. Is that clear? The only thing that we need to measure is the time of flight, the maximum vertical height by calculation, the horizontal range by calculation, and the horizontal range by measurement. So how are we going to do it? Let's go to the simulator. Set to 20. No air resistance. Gravity is 9.8. And we are going to use a cannonball. Okay, not a football. Fire. And once you have your projectile, you can zoom in. Okay, let's zoom in. You want to measure the horizontal range and the time. So how do you do that? You take this, okay, place it at the end of your projectile, and copy the time and the range. Is that clear, Shabab? Copy the time and the range. Go to your data sheet. What is the time? 1.72. 1.72. What is the maximum range measured? 31.24 and recorded. What about maximum vertical height and horizontal range? You have to calculate based on this rule and this rule. Any questions? Any questions, Shabab? Hello? Everyone is sleeping? Come on. It's a nice weather for sleeping, I know. So what you will do after you've recorded 25 degrees, okay? Change the angle. What's the next angle that we have? 30 degrees. Fire the cannon. Make your measurement, okay? But then 45 degrees. Fire and measure. Okay, what's the next one? 60 degrees. I think it's 60. Let's look at the table. Yes, 60 degrees. Fire and measure. And finally, 75 degrees. Okay, fire and measure. And do all the calculations. Okay, everything that you need is in this software. So we will not do all the measurements now. Instead, you will do it. Well, we will do it now, but not together. You will do it for each student. Each student will set his own angle and his own measurements. Any questions, Shabab? You will fill this table according to your own measurements. Any questions?
No, teacher, thank you.
Okay, did you open the link right now, or you need to go outside the Blackboard?
Teacher, can you send it at Telegram?
Okay, I will send you the link, and also I will send you, there is an offline version. You can actually download this one. Let me see. Where is it? Let me open it. You can actually download this one, okay? I forgot where to find the download button. Oh, you have to go to the main website. Let me go to the main website. This is the main website for all the physics. There is chemistry, there's biology if you need, of all the simulation. There is math, okay? It's actually very interesting. And you can search here if you have, wallahi, if you have problem in theory and you want to see it visual, you can go to this website and search for it if they have the simulation, okay? This is the projectile motion, okay? And you can download it. And once you download it, you put it in your tablet or in your laptop without internet, it will work, okay? I will send it to you. If you need from the mobile, they have a version for Apple App Store and also for Google Android phone for Google Play, okay? It's actually very, very good website for simulation. Anyway, I'm sending you the link now. Let's go to home, projectile motion, copy. I will go to chat and send you the link. Okay, any questions how to fill the table? If not, we will let me continue the discussion because you still have this, okay? No questions? It's actually easy. It's like playing, huh? It's like a game. But it is designed by the University of Colorado, so it's actually very professionally done. So what about this? This is only notes, Shabab. This is only notes. You don't need to calculate any from here. You will use this to calculate here and here, okay? Let's go down. What about the graph? Okay, what about the graph? You have to make a graph on paper, and you have to draw 3 trajectories: the angle 30, 45, and 60. Now, I can make it easy if you want, or we can make it hard. To make it easy, you have to graph by hand. How to graph by hand, I can show you a video clip, which I did, how to graph it by paper, okay? Or we can make it easy. You can simply go back to your simulation. This is our simulation. Okay, and you can simply take screenshot of this, and then in your screenshot you put your name or your ID number. For example, let's do a screenshot. Okay, I'll use my snipping tool like this, and then put your name and your ID number. Okay, that's my employee number. Something like this, or you can type it, and you can attach it as PDF to your report and submit it. Which one you want? Which method do you want? Screenshot, or you want to make the graph by what do you call this one? By pencil.
Screenshot is better, teacher.
Of course, it's easier for you. Sir? Okay.
Yes,
So
yes.
I will let you make the screenshot if you promise me that you will submit the report as soon as you will finish it, and not make 1 week waiting. Okay?
Okay.
Okay. Okay, good. Let's go back to the lab report because it's not complete. We have to talk about the source of error and precaution. Okay? Source of error and precaution. Number one, I already told you, air resistance. What is the source of error for air resistance? If we actually do the experiment in the lab, I want to show you what's going to happen, okay? Let's say that we are in the lab, and instead of a cannonball, we are using a golf ball, which is actually small, okay? But there is air resistance. And the velocity is actually small. It's 3 meters per second, okay? Let's try and shoot it at 45 degrees. And what's the effect of air resistance? Let's start without air resistance first. Whoa, it didn't come out of the cannon. Let's increase. Let's make it 10. There you go. Okay, let's zoom in. That's 10 meters per second, 45 degrees, golf ball. With air resistance, what's going to happen? You can see that there is a small difference in the range. Can you see the difference, Shabab? If you take an object with the same mass but increase the diameter, okay, what's going to happen with and without air resistance? Okay, that's without air resistance. With air resistance, increase the diameter. That means the ball is bigger, but the mass remains the same. There you go. Because air will apply more friction to the ball, therefore, the distance that it will travel will be less. Even if you increase the initial speed, okay, let's go 20. Without air resistance, whoa, it's too far, right? With air resistance, there, you can see the difference. Because air is actually pushing against the projectile. Therefore, the range that it will reach is going to be much less. This is the reason why, you know, bullets are shaped so that it will have less air resistance. The front of the bullet is actually very small so that it will have less air resistance. Okay? Now, what else should we do? Let's go to the source of error and precaution. How do you remove air resistance in this experiment? You have to do the experiment in vacuum. In some university, they have a special equipment where they do projectile motion inside a room without air. They take a vacuum pump and remove all the air from the room before they conduct the projectile motion experiment. Okay, so that's the only way to remove air resistance. Or we can do just what we did by using simulation. What else is a source of error here? There is also friction inside the launcher. Okay, let me show you the launcher. Inside this device where we place the ball, there is also friction. The ball will actually touch the barrel of the launcher. Okay, and this friction will also affect the projectile. So that's one other thing. What else is, what's the precaution for the friction inside the launcher? You have to reduce the friction in the launcher. How do we do that? By putting lubrication. Okay. What else is a source of error and precaution? Actually, in the book, just like the other experiments, you will find some precautions. Let's go down here. These are some of the precautions, okay? But because you are not doing it in the lab, I will not let you use it. Of course, these precautions are correct, but we didn't use them, okay? Wear safety goggles. If we do the experiment in real life, you have to wear safety goggles. Do not place other objects in the launcher. That's true. Do not look into the launcher. That's dangerous. You might get hit in the eye. What else? Do not aim the launcher at others. You have to fire the ball or the projectile at the minimum speed, okay? Because in the lab, if you use the maximum speed for the projectile, you will hit the cabinet and break the glass, okay? But this one, you can use it in the simulation. Measure the launching angle accurately, okay? This one is okay, but you cannot use it. So number 6 is a good precaution. What does it mean in number 6? When we say, for example, in the beginning, you have to launch the projectile at 25 degrees, and you make it 26 degrees. Will it make a difference? Of course, okay? Let's launch at 26 degrees. Fire. So that's launched at 26 degrees. What about we launch at 25 degrees? While there might be a small difference, you can see here on the right that there is actually big difference. So you have to set the angle correctly, okay? That's the source of error and the precaution that we are going to write. So at the end of the report here, let's go to source of error and precaution. Where is it? Where is it? Here you go. What is the source of error? The angles are not set correctly. Okay, and what's the precaution? You have to set the angles correctly. Finally, before we finish, last question. At the end, you have to answer the following questions. At what angle will be the horizontal range maximum? You have to find out. Okay? Next, the magnitude of which component do not change? Is it the horizontal or the vertical component of velocity? Which of them do not change? I already showed you in the simulation. If you want to see it now, let's try again. Go to vectors, components, velocity, launch. Which component doesn't change? Tell me. You can see it here. Which components, oh, it's too high, doesn't change? The horizontal or the vertical one? Okay? You should be able to answer that from the simulation. What else? The path of the projectile, is it linear, parabolic, or circular? Answer these 3 questions, attach your screenshot for your projectile trajectories, and you are done with the report. I told you, this is easy peasy lemon squeezy. Any questions? Hello?
Doctor,
Yes, go ahead.
what about percentage error in the table?
Okay, the rule for the percentage error is actually quite easy. It's given to you. In table 2, okay, in table 2, the rule here is not given for the percentage error, right? But in table 1, it's actually given. Calculated minus measured over calculated. This is the same rule for the percentage error in table 2. So you will start with calculated minus measured over calculated. Let's go to table 1. Percentage error. Which one is calculated velocity? Hadi. So you have VO prime minus measured. VO over VO prime, 100%. Absolute value. Okay. That's the rule for percentage error here. What about the percentage error here? We are talking about percentage error in horizontal range. Percentage error in horizontal range. Same thing, calculated minus measured over calculated. So it will be xcal minus x measured over xcal multiply 100%. But I will tell you a secret. Maybe here you will have a small percentage error. But here, your percentage error will most likely be 0. Why is that? Because we are using simulation. And when we are using simulation, there is very small errors. There is no air, no friction. Clear? But still, you can show the calculations or show the answers from here. Any other questions? Shabab, any other questions? I will send the link to your chat, okay? If you have questions, I will stay with you for the next 2 periods because we have 3 periods. You can do the report now, or if you think you can do the report and the simulation without having questions for me, then you can go and you can leave. But before you leave, I want to check the attendance one more time. Anybody who was late or absent from the first session, we will see what we can do for you, okay? But I don't need to record. Well, I can record the attendance on the Blackboard, no problem. So let's